Ничего не могу сказать, у меня нет мнения.
Okay. So let me remind you sort of where we were when we left off at the end of yesterday. We were looking at sort of some relatively simple data. So C was a compact complex curve. We had a quadratic differential. And we had a phase. And so given this sort of rather basic set of data, we were constructing various auxiliary things. And in particular, we constructed on the one hand these things that we called the S-walls.
S from surface.
S from soliton. Yeah, this is a little bit of legacy from the physics. So yeah, S is for soliton. It could have been for saddle, but sometimes they're not. I mean,
Since you insist that they go through zeros, that's sometimes.
they go. Okay, they do go through a. Okay, we will have more general S-walls later today, which will not go through. Yeah, so we had these S-walls, and we had something that I called the path lifting rule. Okay, so this is a very short resume, and now let me remind you a little bit what these things were. Actually, let me add one more item to that list. So we had the S-walls, we had this canonical double cover, spectral curve, double cover of C that was determined using 2, and then we have this path. So I won't rewrite all the definitions, but remind you of what the relevant pictures were. So what the S-walls were was this quadratic differential had a bunch of zeros, and from every zero there emerged 3 canonical trajectories. So these trajectories are leaves of a globally defined foliation. So they're solutions of some differential equation. And because they're all leaves of the same foliation, they never cross each other. So there's some picture like this. They either wind around the surface forever, or they wind up at punctures. In the case where this quadratic differential has a pole, all these S-walls eventually wind up at the pole. So these were the S-walls. The zeros of phi 2. And then this path lifting rule was a kind of complicated beast. But at least what kind of thing was it? So the path lifting rule takes paths P on the curve C to, if you like, Z, so to sort of formal Z linear combinations of paths on sigma in a way that's on the one hand compatible with composition, and on the other hand, so this property would be satisfied just by the most trivial kind of path lifting, where you just lift every path to all of its pre-images upstairs. But the other thing was that it had this kind of twisted homotopy invariance. So we called this formal Z-linear combination of paths. We called paths on sigma to formal linear combination that depends on sigma, which we call f of p. So even the existence of such a rule is a little bit non-trivial. But now I want to use it for something, and so the strategy So this rule depended on the S-walls. And now, so as I described last time, what we're really interested in this business is how the S-walls change when we vary the parameters theta and phi 2. And in particular, what we saw in pictures last time is that so as we vary these parameters theta and phi 2, the S-walls, they vary. Now for small changes of theta and phi 2, they just vary by some kind of continuous isotope. You know, you just rotated this picture a little bit, but its topology doesn't change. But there's some critical phases where the topology does change. So they change their topology at the theta phi 2 where there exists a special trajectory. So the special trajectories were or a special S-wall, if you like. Special trajectories were these ones or these ones. Okay. So the idea is now to use that use this kind of topology change to study these special trajectories, in particular to prove this wall crossing formula, which I stated last time and won't restate now. But to be specific, so at the moment when the topology of the S-walls change, this path lifting rule will also change. So when the topology of S-walls changes, this path lifting rule will also change. And it's by studying that change that we're going to discover the K.S. wall crossing formula. So okay. So in fact, this path lifting rule from P to F of P is quite a lot of information. We wanted to find something that uses a little bit less. I said this at the end of the last lecture, but I said it rather quickly. So in fact, we can study a sort of reduced, a closed version of F of P. So if P is a closed path on C, then we define T of P. We define T of P by we define T of P by starting with F of P and dropping all non-closed paths. Remember, the picture is we have some closed path P downstairs on C, F of P upstairs. So P is a closed path, but we think of it as a path with a definite initial and final point. So this point Z then has various lifts, sorry, two lifts, Z1 and Z2 upstairs. And then F of P is some linear combination of paths up here. Some of them go from Z1 to Z1, some of them go from Z2 to Z2. Those we keep. The ones that go from Z1 to Z2 or Z2 to Z1 we drop. So that's what I mean by T of P. I just drop all the non-closed paths, and then moreover, And then I pass from homotopy. So then we only remember the homology classes of the surviving closed paths.
And the fact that you drop the non-closed path, doesn't it spoil the compatibility with composition?
Well, yeah, now I'm not saying anything about compatibility with composition anymore. So the F of P has a great composition property.
No.
And now I'm just defining something separate, which I call T of P. And
No, if you choose another starting point from the same closed path, do you get the same?
yes, it'll be the same T of P. I think, okay, I've never thought about how to prove it, but I think that would follow from the compatibility of F of P with homotopy, yeah. So morally, this is really, okay, later we'll see a precise sense in which this is really like taking the trace of some holonomia around this. Okay, so that's T of P. So let me give you an example of that because it might seem a little bit abstract. So let's suppose we're in the following situation. Suppose we're on the cylinder. Well, globally, C doesn't have to be a cylinder. I'm just going to draw part of the picture. Part of C has a cylinder in it. And let's suppose that we have... let's suppose we have just two branch points. Two zeros of the quadratic differential sort of in play here. So one of them up here, and one of them down here. Like this. This whole thing is on the cylinder, and I take P to be a path that's going around the cylinder like this. So both of these things are happening on the front of the cylinder. The only thing that happens on the back of the cylinder is that I'm winding back around. So this is a closed path. And now we can ask, what will F of P look like and what will T of P look like? So remember how this path lifting rule works. The rule is that you take all possible lifts of this thing to its twofold covering, with the additional rule that whenever I cross an S-wall, I'm allowed to take a detour, where I go down to the branch point and come back on the other sheet. So there's two sort of obvious terms that will occur in T of P, where I just don't take any detours at all. I just lift this thing up, I just lift it up in the most obvious way to one sheet or the other. Now on this picture, I should really, well, okay. So let me represent now, here's the original path P, and now I'm going to represent T of P over here. So it's going to be a sum of three terms. And now I don't want to draw the covering directly. I'll just think of it as a branch cover of, well, I think of it as a branch cover in the usual way, so I'll just draw one or two for things that are on the first sheet or the second sheet. And the sheet labeling is defined on the complement of these cuts. So when something goes through a cut, it moves from sheet 1 to sheet 2. So there's going to be three terms. One term is just this on sheet 1. Then there's a similar term where we just go on sheet 2. Now then there's terms where I take one detour or the other. But those terms will wind up on the other sheet. So if I take a detour, I wind up on the other sheet. And so when I come around, I come back to the other sheet. So that's part of F of P, but doesn't contribute to T of P. T of P is only the closed length. So there's one more way of getting a closed thing, which is to take both possible detours. If I take both detours, I wind up back on the original sheet again. And so this third term, what it looks like, well, the simplest way of thinking of it is, so I go along here on, say, sheet 1, then I take this detour, I can just deform that to look like this. So this is a thing which starts on sheet 1, then it's taken this detour, now it's on sheet 2, now it's back on sheet 1, and it comes back around on sheet 1. So this is, so separate these three terms. One term, two terms, three terms. So these are three different homology classes on the covering. So T of P is just the formal sum of those three classes. I don't add them in homology. I just add the formal variables in my group ring corresponding to this homology class, this homology class, and this homology class. So that's what kind of thing T of P is. It's something totally concrete. Okay.
Do we assume here that there is an intersection of the cycle only with this separate trace length, and no intersections with other ones, right?
No intersections with other S-walls.
I see.
Yeah, that's right. So there may be a million other S-walls elsewhere on this curve C, but I'm assuming that in this part of the curve C, the only S-walls are the ones that you see here. It's still confusing.
I'm confused. How do you decide why you use or not use this or that S-wall? So here, the S-walls which you use, there are two S-walls which seem to be privileged.
Oh, why didn't I use these ones?
For example, or some other ones.
Well, the path, my path P, I have a very specific path P here. Had I used some other path which crossed some other S-walls, I would have used those. But here I've got this particular path, and so I use only the S-walls which are crossed by this particular path.
So this path doesn't cross any other S-wall?
That's right. This path crosses only these two.
Okay.
The first lift there, shouldn't it be a lift of a path, not a cycle? Isn't it a lift of something that doesn't?
So I defined the lift both for open things and for closed things. But now this traced object I define only for closed things. So you can think of it as I first take this open thing, which just happens to begin and end at the same point. I lift it and I find these three terms plus actually two more, which would be non-closed. But then, so that would be f of p for this p. But then, in order to passing the t of p means that I drop the ones that are not closed, and I keep only these three.
Could you explain why, if you replace on the last picture letters 1 by letter 2, it will be not in the...
Okay, so you want me to here put 2, 1, 2 instead of 1, 2, 1? Okay, very good. So that was a detail that I kind of compressed. So these S-walls carry a little bit of orientation on them. So they're not oriented on C, but if you lift them up to the cover, they're naturally oriented because they're trajectories of the quadratic differential. And so there's a rule here which says when you take the detour, you're only allowed to take a detour which is oriented, I think if I remember my conventions right, oriented opposite the S-wall. Anyway, that'll prefer one or the other, and then I arbitrarily chose to call it 1, 2, 1. Yeah.
So you choose one of the two square roots and you fix it forever.
Well, upstairs, on the covering,
upstairs.
the covering canonically carries a square root, right?
There are two of them.
No, covering is 1 form. Covering is
And mine is 1 form.
no, this is 1 form.
How do you distinguish between one form and one is
It's one different project.
So you choose one of them?
No.
So the covering is
a choice of square root. It's not the square root.
No, that's what I'm saying. You have to choose one of the two square roots.
There's 2 points, but on the covering this is 1 form, canonical 1 form.
So here's my definition of the covering. If I define the covering in exact, sorry. If I define.
Okay.
Okay, great. Yeah, so this is an example of the kind of thing that you do. So you have some path and you lift it to a bunch of closed paths, but it might not be just the obvious ones. I mean, there can really be extra things that appear. So now we ask ourselves the following question. That clearly depended on the structure of the S-walls. Had there been no S-walls there, this third term wouldn't have appeared. So how exactly do these T of P's depend on the configuration of the S-walls? In particular, how do they change when the S-walls drop? So let me show you an example of that. Sorry, yesterday did I call this F of P or L of P? Sorry. So how does, in fact, it's just as easy to describe it first for L of P. How does L of P jump as the S-walls change? Well, let's look at the simplest example of that S-wall changing phenomenon. Namely, we can think of the following thing. So imagine I have two branch points like this, and I have, in fact, let me put them just aligned, like this. And suppose I have two S-walls which come quite close to each other and then sort of veer off like this. So this is a typical picture very close to where one of those saddle connections occurs. So here we can have some path that goes through this thing. And so we can compute L of P for this. And then we can compare it with what we get by doing it the other way. With what we get after we've... So if we vary theta a little bit, or vary the quadratic differential a little bit, we can reach this situation, where there's been a topology change. And then here too, so we have the exact same path as before. So P hasn't changed, but we calculate L of P in these two different situations. And what will we get? Well, okay, so let's divide these two things. So L of this situation is going to be a sum of 5 terms. L of this situation is going to be another sum of 5 terms, and we'll compare them. Well, the first two terms are pretty simple. So there's one term where the thing just goes through on sheet 1, doesn't take any detour. There's another term where the thing just goes through on sheet 2, doesn't take any detour. Then so just continuing it down here. So then there's terms where we take one detour or the other. So we're crossing two S-walls up there. So one possibility is to go around to the left, take the detour to the left. So then we start out on sheet 1 and wind up on sheet 2, because there's a branch cut here, so we've switched to the other sheet. Then we can have another one where we start out on sheet 2 and take the detour to the right and wind up on sheet 1. And then finally, there's the fifth term, which is a really interesting term, which is one where you take both detours. And this one actually depends on the order in which you meet these two walls. So here, if I start out on sheet 1, I'm going to meet the left one first. So the fifth term is one which starts out on sheet 1, goes to the left, then comes back to the right, and then and comes back on sheet 1 again. So it's like this. So it starts on 1, ends up on 1, but it does it by going around this kind of complicated thing. Now, on the other side, what do I have? So after the S-walls have gone through this little transition, well, these first two terms, of course, are exactly the same. They didn't care about the S-walls at all. These two terms are also the same. They use one S-wall, but they don't care what the relative ordering of the S-walls is. But finally, there's this last one, this last path. And the last path now is different because it has to go first to the right and then to the left. Because up there, those walls, you first meet the one that came from the right and then you meet the one that came from the left. So this one now goes like this. And that makes a big difference. It means it has to start on sheet 2 and end up on sheet 2. So this is a totally different path. Okay. Okay, so my path lifting rule has changed a little bit. Before it had a term like this, that was on sheet 1, and now instead it has a term like this on sheet 2. So how do I understand so I want to write some kind of formula that captures this behavior. So right, so I wrote something for this right, so here I showed you for some particular path P. So now how? So general formula. For the jump of L of P. Well, there's some critical locus where the action is happening. So let me call this locus S. So if I have a path that does not cross S at all, then nothing happens to it. If P doesn't cross S, then L of P doesn't jump. If, on the other hand, P does cross S, well, as usual, I can kind of break the thing up by composition, so I can just look at where if it crosses S in a single place. If P does cross S in a single place, so then I claim that this computation that I did by hand over there can be summarized in just a simple formula, namely. So I divide P into the part before S and the part after S. So let's call it P1 and P2. Yes. Right. Yeah. Sorry. I want to state this slightly differently. Yeah, if P does cross S, right. So then its jump is given by a kind of universal formula. A universal formula which you can actually express without knowing anything about what the path is at all. It's universal for every path. All it is a transformation, so a universal transformation acting on L of P. So L of P is some sum of paths upstairs, some sum of paths on sigma. And I'm just going to give you the transformation acting directly on the paths on sigma. Right, so for any path, I'll use little a for the paths on sigma. Which meets P once, which meets S once. Any path on sigma which meets S once.
Actually, double color fit.
Well, that's right. Which meets the which meets the lift of S. Let's call it pi inverse of S. Pi is the projection from sigma to C. So for any path on sigma, so now I'm drawing the path upstairs, but the picture will be similar. So I'll divide it into two parts. Let me call them A1 and A2. And they're separated by this S. So we have to make the following transformation. So the original path A, which was A1, A2, gets transformed to, so again we have A1 and A2, but now we stick something in the middle, and the thing we stick in is simply so now we're going to have two terms. We're going to have two terms. One is just the original A1, A2, and the other one is A1, A2 with inserted a little path that goes around pi inverse of S. So let's see how it happens over here. So first, let's look at these two terms. So this term, this path that goes from 1 to 2, this one you can see actually has no, this term has no intersection with the lift of S, because you can homotope it so that it goes over here. And so that term just survives unchanged over here. This term, similarly, this is some path on sigma that has zero intersection with the lift of S, because it can be homotoped over to here. And so that term just survives over to here. Now let's look at the terms that go from sheet 2 to sheet 2. So on this side, we just had a single term going from sheet 2 to sheet 2, namely this one. On the other side, we have two such terms. We have the original term, that one is here, plus another term going from 2 to 2, which is this one. So it differs from the original one just by adding this little loop, which is actually just a copy of the preimage of S. This is exactly the closed loop that the saddle connection lifted to. So that term there has been transformed into a sum of two things, which is exactly what you get from this formula, using the fact that the intersection number of that path with S, assuming I've chosen, sorry, this is also the intersection of A with pi inverse of S. So if I look at this path A, this path here, it has intersection number 1 with the lifted S. Now, on the other hand, what happened to the other terms, the terms that went from 1 to 1? So there I had two terms up here. I had this term and that term, and on the other side, this extra term has disappeared. Well, that's exactly the effect of dividing by 1 plus pi inverse of S.
So this intersection number in yours, it's plus minus 1 because
It's plus or minus 1, that's right. So this is always plus or minus 1. It just keeps track of whether you're gaining that extra loop or losing it. But it can only be written in this kind of universal form. So to make a long story short, so there's some universal rule that tells you how these path lifting things change when you hit a saddle connection. And the way that they change is just roughly by inserting or deleting copies of that saddle connection in the lifted paths. So that's exactly what we were doing here. We were either inserting or deleting a copy of this thing. Okay. So and it's sort of universal. So all L of P. So regardless of what the path is, all the L of P's are simultaneously modified by this same single transformation, which just acts on the sort of image. Are simultaneously changed by this same transformation as the R2 across the locus where the saddle connection exists. Okay. So now that we have this information, it's sort of easy to see what will happen to those traces. So I defined something that I called T of P, which was just obtained by taking these L of P's and kind of closing up the ends. So that's very similar. Just basically take the trace, do this transformation, and then take the trace, and what you get is I'm calling this operation of dropping the non-closed ones, I'm calling taking the trace. But anyway, this implies that all T of P, so all F of P jump, all L of P jump by this universal thing. So all T of P also jump by a universal thing. So now I write it in terms of closed paths, and in fact just homology classes of closed paths. It only depends on the homology class. we just add, sorry, we just multiply it by 1 plus, now I have the homology class of the closed cycle, the charge of this saddle connection, and again to the power symplectic product, again with gamma S. So before, when I wrote this intersection number here, it was sort of the actual intersection of one particular little open path. And that certainly depended on the details of that open path. But once we pass the closed paths, it's just the intersection in numbered homology that appears. So this is a sort of simple thing. So what is this? So this is a transformation that we saw before. So this is exactly the transformation that we called K gamma S last time. It was the transformation that appeared in the Kontsevich-Soibelman formula. It was exactly the transformation that Kontsevich and Soibelman would have assigned to this saddle connection, this thing that has Dons and Thomas invariant equal to 1. So now we see the sort of geometric origin of that, well, at least in this one way of understanding the geometric origin of this transformation. So there's a second example, of course. So we know that these saddle connections aren't the only thing you can think about. We should also think about these the case where we get a closed trajectory.
Andy?
Yeah.
Could you remind me for a moment what the two products on the right-hand side of that formula are?
Thanks. So here, this is the product in sort of the group ring on homology. So, so here I'm thinking, when you see gamma times gamma S, this means the composition of, it means what you usually call the sum of those two homology classes. And here, on the other hand, this is just the usual intersection pairing. And all this is taking place in the sort of group ring over that homology. So I'm taking formal linear combinations of homology classes.
And we're going to homology get